All right, in this video, we're going to very quickly go over integrals and integral calculus. So the crash course version of integrals. Now, the way that we write an integral is we put a big curly S, then the thing we want to integrate, followed by dx or dy or whatever, d this thing that we're integrating with respect to. So that dx right there is just saying I'm going to integrate this function of x with respect to x. And if the function was a function of other parameters, we're doing this integral with respect to x. That's what the dx tells us. Now, the integral is the inverse of the derivative, sort of. So if I take the integral of f dx, and then I take the derivative of it, as shown here in the top equation, if I take the integral of f and then take the result of that and take the derivative of that, I get f back, all right? If I take the derivative of f and then I integrate that, I get f back almost plus a constant. Why a constant? Well, let's consider this. What is the integral of 3x squared dx? Well, what do I have to take the derivative of to get 3x squared? Oh, that's just x cubed, right? The derivative of x cubed is 3x squared. So the integral of 3x squared must be x cubed, because that's the thing I take the derivative of to get 3x squared. But, right, so the integral of 3x squared dx is x cubed because d dx of x cubed is 3x squared. But the derivative of x cubed plus 4 also equals 3x squared. And so does the derivative of 3x squared minus 7, and 3x cubed plus y, and 3x cubed plus 4 pi. Because remember, when we take derivatives, the derivative of a constant is 0. So if I take any of these statements here, any of these functions, x cubed plus anything that is a constant, and I take the derivative of that, I'm going to get 3x squared. So when I integrate to go backwards, to go back to my original function, I've lost that constant. I don't know what that constant was. So when I take what we call an indefinite integral, the solution we get is always something that we find plus a constant. Now, so integrals are kind of like inverse derivatives, but integrals are also infinite sums. So as you remember, when we talked about derivatives, we talked about velocity. And the average velocity of something is the change in distance divided by the time it took to change that distance. But then you can solve this equation for x, and you could say the distance that you travel is just your average velocity times the time you were traveling. Well, if you have a velocity that's changing with time and you want to find how far you went, one thing you could do is you could break up your journey into tiny little pieces, infinitesimal pieces. So we're going to take this equation right here and turn delta x and delta t into infinitesimal steps. So now it's dx is equal to v times dt. And we no longer have the average velocity because for that infinitesimal step of time, the velocity doesn't change. Now, if I want to find the total delta x of my journey, I just have to add up all of these little dx's, all infinite number of these infinitely small dx's. So delta x is just the sum of all of these dx's. In the limit, as dx goes to 0, the sum of all of these dx's is precisely what the integral of dx is. So the integral is an infinite sum of infinitesimally small things. Well, now I know, right, that dx is just velocity times dt, so the change in my position is just the integral of dx, which is the integral of v dt, so I could just integrate v dt and find how far I traveled. And we can show that that's true because we know that the velocity is just, the instantaneous velocity is just dx dt, so if I plug that in for v, now I've got the integral of dx dt, and that's taking the derivative of something and then integrating it. We should get the original thing back, right? Plus a constant. So we get x plus a constant. So the distance we traveled is x plus a constant. So the change in x is x plus some constant. What is that constant? It's negative our initial position, because change in position is where we are now minus where we started. Now, what we've been showing so far are what we call indefinite integrals. So indefinite integrals look like this. I take the the integral of something, like for example, I could take the integral of 3x squared times dx, and we said, oh, that's equal to x cubed plus a constant. That's an indefinite integral. In a definite integral, we look at a range over which we integrate. So when we did our indefinite integral, we said, well, delta x is the integral of v dt, but how much the distance changes depends on what time range we're considering. So for a definite integral, we give those ranges. We say, I'm going to start at this time, t initial, and integrate out to this time, t final. All right? When we evaluate our definite integral, all right, so the integral from t initial to t final of a t squared dt, well, a is just a constant, right? And a over 3 t cubed is the thing I take the derivative of to get a t squared, as you'll recall. So if I take the derivative of this, I get this. And so the integral of this must just be this plus a constant. But when I do a definite integral, I don't have to worry about the constant, and you'll see why. So I do this integral, and I get this result, but then I draw a line, and I say, hey, this was a definite integral, so the answer I'm going to get when I evaluate it is this thing evaluated between t equals t initial and t final. Now, how do you evaluate something between an initial and a final state? Well, what you do is you just take whatever you got and evaluate it at the final time, and then subtract that same thing evaluated at the initial time. So this bar right here with t equals t initial to t final, it just means plug t final into here and then plug t initial and subtract the two. So there's my answer. So when I do definite integrals, I don't have to worry about the constant because I get the same constant when I do evaluate the initial and the final point. And so when I subtract them, the constants subtract out, they cancel out. All right, so integrals are sums. Here's another example of using an integral to do a fancy sum. So let's say I want to find a formula that gives me the volume of a pyramid. Well, what I'm going to do is in my mind, I'm going to slice this pyramid up into little slices, okay? Now, eventually I'm going to take the limit as the thickness of each slice goes to 0 and the number of slices goes to infinity. And when I do that, then I'm just adding an infinite number of infinitesimal things. So I'm going to add this little bit of volume, d volume, and I add all those little d volumes together to get the total volume. So volume is just the integral of d volume. But what is the volume of one of those slices? What is dv? Well, first, we need to come up with a coordinate system we can use to label our slices. And for this problem, I chose to label each slice with its height above the ground, and I'll call that y. Now, if I look at just one of these slices, this slice here in red, if I pull it out and flip it over, you can see that this slice is basically just a square, but then it's got some thickness to it. Now, the edge of my square is beveled because the square at the top of my slice and the square at the bottom of my slice, they have a different side length. But in the limit, as I have an infinite number of slices, that difference between the side of the top and the bottom of my slice, that will go to 0. So we won't worry about that, and we'll just say, well, hey, the volume of that slice is just the area, which is w squared, times the thickness, and the thickness is just dy. That's a little change in y as we go up and integrate. So dv is just w squared dy. So if I can just integrate w squared dy, I will get my volume. But w depends on y. So in order to do that integral, I have to know what w is as a function of y so that I can integrate it with respect to y. Well, this is w as a function of y because I know at the top of my pyramid, that width should go to 0. And so when y is equal to h, this goes to 0. At y equals 0, I should just get the length of the bottom, which I'm calling L, all right? And so I need something that linearly goes from L to 0 as y goes from 0 to h. And this is the thing that does that. This is the equation of a line that has the endpoints, the proper endpoints, such that at y equals 0, I get L, and at y equals h, I get 0. So there's w, so I can just plug that into my dv, and then plug that into my integral, and I'll find then that the volume is the integral of L squared times 1 minus y over h squared dy. So this is just the area, this is just the volume of one slice. All right? That's the volume of one slice. And then I'm going to integrate from 0 to h, right? Because that's where I start. I go from y equals 0 to y equals h. If I integrated past h, this equation would start to give me negative volumes, and that would be wrong, right? I'm integrating past the end of the thing I'm trying to find the volume of. If I let y go negative, that doesn't make any sense. Because my pyramid doesn't extend down below y equals 0. So I put the limits in here, and when I'm done, I'm not going to get something plus a constant because this is a definite integral. I'm going to actually get the volume of the pyramid. So all I have to do to find the volume of a pyramid is evaluate that integral. But how do you evaluate that integral? Okay, now we know what integrals are good for. We've seen how to set up an integral to solve a problem. Let's talk about some of the things you need to know to solve integrals, to evaluate integrals. Now, evaluating integrals is generally harder than evaluating derivatives. And sometimes you get stuck and you just can't evaluate an integral. But we'll show you some tools that will help you be able to evaluate different types of integrals. So the first thing you should know is in this class, there are 4 kind of basic building block integrals that you need to know. First of all, up here, the integral of x to the nth power is just 1 over n plus 1, x to the n plus 1 plus a constant. Right? If I take the derivative of this, the constant goes away. X goes from x to the n plus 1 to x to the nth power, and we multiply by an n plus 1, and that cancels out the 1 over n plus 1, and we get x to the nth back. All right? So because we know how to take the derivative of 1 over n plus 1 times x to the n plus 1 plus c, we can see right away that, yes, that is the integral of x to the nth power. Similarly, the integral of sine is negative cosine plus a constant, because if I take the derivative of negative cosine, I get sine. And the integral of cosine is sine, because if I take the derivative of sine, I get cosine. And of course, the derivative of natural log of x is 1 over x, so that means the integral of 1 over x dx is just the natural log of x plus c. Now, if you look up here, n can be negative, and so the integral of 1 over x, that's the same as the integral of x to the negative 1 power. So maybe you think, well, we could just use this one. But look what happens when n is equal to negative 1. I get x to the negative 1 plus 1. So x to the 0th power, that's 1. All divided by negative 1 plus 1, 1 over 0. Whoops, I've got an infinity. I've got a singularity. So it turns out that 1 over x is the exception where this top one doesn't work, and we have a special integral for 1 over x. These are the ones that you will need for this class, and using these basic integrals and some techniques I'm about to show you, you'll be able to do what you need to do in this class. But as you take your calculus classes, you will find different ways to evaluate other integrals, which will show up in other places. All right, so in order to use those basic building blocks to integrate more complicated things, there are some integral properties you should know. First of all, if I take the integral of a constant times a function, that's equal to the constant times the integral of the function. Constants come right out of the integral, okay? Another thing you should know is that the integral of a sum of things is just the sum of the integral of each individual thing. So I can take an integral of a sum and turn that into a sum of integrals. So, for example, if I wanted to integrate 12r cubed plus 7r with respect to r, the first thing I'm going to do is I'm going to say, well, look, it's the sum of two things, so I can break this up into two integrals. This is equal to the integral of 12r cubed dr plus the integral of 7r dr. Next thing I'm going to do is I'm going to say, well, each of these has a constant in them. I can pull them out. So this is 12 times the integral of r cubed plus 7 times the integral of r. And then r cubed and r, I know how to integrate them. They're one of my basic types. The integral of r cubed is just 1/4 r to the 4th, and the integral of r is just 1/2 r squared, and then plus a constant. I only need one constant when I have two integrals, right? If I had two of them, I could just join them together into, so now they're, some unknown thing, all right? And then I can simplify this, and I find that my integral is 3r to the 4th plus 7/2 r squared plus a constant. Another trick that helps you do a lot more integrals is something called a U substitution. And the U substitution, I'll show you that by example. So imagine, here's the integral we wanted to do to find the volume of our pyramid. And we look at that and we say, it's not one of our types of integrals that we know how to do. What can we do? Well, the first thing we'll do is, since L squared is a constant, we'll pull that out, and then I just have to evaluate this integral. And I look at this and I say, this is kind of weird. I don't know how to integrate that. But what we're going to do is we're going to define a new variable. I'm going to define u to be equal to 1 minus y over h. So I take this thing right here, and I'm just going to call that whole thing u. Then I take this, and this integral here now is just the integral of u squared dy, right? This looks a lot simpler. I know how to integrate u squared with respect to u, but how do I do it with respect to y? Well, what I have to do is I have to convert the dy into a du. And the way we do that is I'm going to take my definition of u, and I'm going to take the derivative of that with respect to y. Du dy is, well, the derivative of 1 is 0. And the derivative of negative y over h is negative 1 over h, right? Negative 1 over h is a constant, and the derivative of y is just 1. So now I can solve that, and I find that dy is the same thing as negative h du. So I'm going to replace that dy with a negative h times du. The negative h is a constant, it comes out, and then the integral of u squared du is just 1/3 u cubed. And then I can just go ahead and substitute 1 minus y over h back in for my u, and I've got my answer. So this is a u substitution. You take something a little complicated and you call that, all one thing, call that u, in order to make your integral something that you can do. Now, you may have noticed that up here we had a definite integral, but I dropped the limits down here. How do we handle the limits when we do a u substitution? Well, there's a couple ways we can do that. So here I'm integrating from 0 to h, but when I get over here, I'm not integrating with respect to y anymore. I'm integrating with respect to u. So what I can do is I can say, well, what is u equal to when y is equal to 0? Oh, when y is equal to 0, u is equal to 1. What is u equal to when y is equal to h? Well, if I plug in h right here, I get 1 minus 1, I get 0. So then I can say, I'm going to plug in my limits for u based on the equivalent limits for y. So when y is equal to 0, u is equal to 1. So I put a 1 down here. When y is equal to h, u is equal to 0. So I put a 0 up here. And then I have this integral. I can do the integral. The negative h comes out. The integral of u squared du is 1/3 u cubed, and I evaluate that between 1 and 0. And remember, evaluating between 1 and 0 means I take this expression evaluated at u equals 0, and I subtract from that this expression evaluated at u equals 1. So this is negative h over 1/3, 0 cubed minus 1 cubed, which is h over 3. And remember, the volume of our pyramid was L squared times this integral. So now we found the volume of our pyramid is just L squared times the height of the pyramid divided by 3. Another way we could have dealt with the limits is we could have not changed them into u and kept them as y limits. So what I'm going to do is I'm going to say, well, look, here are my limits, but I'm explicitly in my limit going to say y equals 0 to h. Y equals 0 to h. And that reminds me, hey, these are not the limits on u, these are the limits on y. So then when I go to evaluate this integral, right, the negative h comes out, and the integral of u squared du is just u cubed, and then I evaluate that, but I don't evaluate that from u equals something to something, I evaluate it from y equals 0 to h. So these limits are on y. Before I plug them in, I need to convert my u back into something in terms of y. So remember, u is equal to 1 minus y over h, so I plug that back in, and now I can evaluate my limits. I'm going to take negative h times 1/3 times 1 minus h cubed minus 1 minus 0 over h cubed. And that is all equal to h over 1/3. And once again, I get the same volume. So you can do it either way. You can, when you do a u substitution, you can convert your limits into the new variable, or you can keep them in the old one, but then before you actually evaluate your limits, after you've done the integral, you have to convert back to your original variable. Another way you can do integrals is looking them up in tables. All right, so you can find various places online and textbooks where they will list a bunch of integral forms. Like you might find in an integral table, the integral of x natural log of x dx is x squared over 2 natural log of x minus x squared over 4. And of course, that's also plus a constant. Sometimes they leave the plus a constant off just to save space because you know if this is an indefinite integral, there's always going to be a plus a constant. So maybe you look this up in a table somewhere, or maybe you're doing an exam or a homework problem and Dr. Durfee says, hey, you may need to know this integral while you're working this problem. And you look at it and you'll say, ah, cool. If I see something that looks like that, that's what the integral is. So now imagine you're working a problem and you have an integral that looks like this. And you say, well, look, if I just replace q with x, it's almost the same thing. All right? And it's okay to replace q with something, right? It's just an integration variable. But it's not quite. If I replace q with x, I still have that k there. Let's assume this k is a constant. So it doesn't quite match the form. So what we need to do is do some sort of manipulation to make my integral look like the integral that's in the table. The way I'm going to do that is with a u substitution. I'm going to define u to be equal to k times q. Well, I have a q here without a k, so I need to note that I can solve this for q. Q is just u over k. So I'm going to replace that with u over k. I'm going to replace that with u. And then I need to replace the dq. How do I find the dq? Well, if I take the derivative of this, I find quickly that dq is 1 over k times du. So I can plug that all in. So q is 1 over k times u. Then we have the natural log of kq, which is just u. And then dq becomes 1 over k du. Now, these 1 over k's are constants, so they come out, and I can write this as 1 over k squared times the integral of u, natural log of u du. And that's like exactly the same as what's in my table here, except with u instead of x. So now I know my answer. It's 1 over k squared times u squared over 2, natural log of u, minus u squared over 4. All right? Where did the k's go right here? Oh, yeah. I'm going to convert back now from u into to q. These x's should be q's, all right? And when I do that, since u is k times q, I'm going to get a k squared and a q squared in each of these terms. So that cancels out the k squared out front, and then I'll just get a q squared over 2 natural log of kq minus q squared over 4. Sorry, I copied and pasted and forgot to change these x's into q's. They should be q's here. Plus a constant, of course, because this is an indefinite integral. Another thing that an integral is an integral is also the area under a curve. So imagine I have some curve, y as a function of x. Well, if I make little slices here, I'm going to make little rectangles, and each one of these rectangles is going to have a certain width, all right, a little change in x, and then I'm going to make the left corner of the rectangle be y at that value of x, right? And then as I make these rectangles smaller and smaller, eventually these rectangles all added together are the area under the curve. So each little slice of area for each of these rectangles, I just add them all up. I integrate each little piece of area and I get my total area. So I add up all these little bits of area, but each little bit of area is just y, the height is y, and the width is dx. And as I take the limit as dx goes to 0, I get my integral, I do the integral, and I will get the area under that curve. Now, in order to get the area under the curve, I need to say what range of the curve I'm finding the area under, and those would go as my integration limits, x initial and x final. So what we've shown is that integrals are the antiderivative, except for a constant. They are also an infinite sum of infinitesimal slices, and integrals are also the area under a curve. The integral of a function is just the area under that function if you plot it. The one that I've used most is thinking of integrals as an infinite sum of infinitesimal slices. If I want to find the volume of something, I can slice it up into little infinitesimal volumes, and I integrate. I add up all those infinitesimal volumes. If I want to find the area of something, I chop up the area and add up all those little infinitesimal areas. If I want to find the total force acting on something, I can take all the little infinitesimal forces acting on it and add them up. If I want to find the mass of something, I can chop it up and add all the little infinitesimal masses and integrate dm to get m. If I want to find the energy inside something, I can break it up into pieces and add up all those infinitesimal pieces. If I want to find the moment of inertia of some object, I can break it up into pieces and add the moment of inertia of all the infinitesimal pieces together and find that using an integral. Now, remember, in general, it's harder to take an integral than a derivative. But once you have taken an integral, you can check your work by taking the derivative of what you got and see if you get the integrand back. The integrand is the thing inside the integral. And once again, remember, there are these 4 basic integrals you need to know how to do. You need to remember that you can pull constants out of integrals. You need to remember that you can break up a sum inside of an integral into a sum of different integrals. You need to remember how to do use substitutions, and you need to understand how to use integral tables. And that is the end of our discussion on integration.